In this video, I hope to share with you the understanding of a open loop canonical form. The open loop is ax plus bu. If you still remember, this is the open loop, ax plus bu, that is going to input into the controller. For a closed loop is ax plus bu, and there's a minus k over here. This is the closed loop. Alright, so therefore in this video I hope to address the canonical form of a open loop. Alright, and later on we can go into the closed loop system. Alright, so in order to show you the usefulness of the canonical form, I'll just with the understanding of this transfer function over here, alright, we gonna use this example to show you the state space system. So I'm gonna copy this thing over here, and I'm gonna paste it all over here. Okay, and instead of writing b and a, I'll just write as y and u as shown over here. Alright, and next is that, alright, this is, I can write s squared as s to the power of 1, and can also write 12 as 12s to the power of 0. Alright, because s to the power of 0 is simply equals to 1, right? So 12 times 1 is equals to 12. And then 2 is s to the power of 0 also. Alright, and therefore it's being all represented over here. Now in order to write state space, okay, I can say that s to the power of 0 is equals to x2. If I were to differentiate x2, I'll get x2 dot. Alright, I can say that s0 will become s to the power of 1. Why? It's because, for example, if you remember, integration is 1 over s. Differentiation is therefore s. Alright, 1 over s is integration, oppositely s will be differentiation. Okay, this is just simply the understanding for inverse Laplace. Alright, but anyway, not inverse Laplace, but I think it's a Laplace transform, sorry. So for integration is 1 over s, for differentiation is s. So therefore if I were to differentiate x2 to x2 dot, s to the power of 0 will become s to the power of 1. Alright, and I can simply write s dot 2 as x1. And now if I were to differentiate x1, I'll have x1 dot, and now s to the power of 1, I'll write as s to the power of 2, because differentiation, s times s. Okay, so therefore I can re-represent all my s squared, my s1, my s0 as my x2, x1, and x1 dot. So yeah, I'll just sub it in now. Alright, so I have these things over here, and in order to write these things in terms of state space, you know that we have a x2, x1, and we also have x dot 2 and x dot 1. So you can simply write the input x1 and x2, alright, which is equals to x1 dot, x2 dot. Okay, or this thing is your x dot equals to your a x plus, maybe I should write plus bu. Sorry, I should have write this as matrix bu. Okay, this is, yeah. Alright, so therefore I have written this as a state space. And remember that you're gonna learn how to do this, because in the exam you're gonna know how to write out these things also. Alright, and therefore what we can do next is that what? x1 dot is simply what? We can take the denominator of this thing, the poles. Alright, because, so I'll just write as x1 dot plus 7x1 plus 12x2 is equals to u. This is x2, sorry, equals to u. Alright, this is your input, this is your output. If you remember, output over input is your transfer function. But anyway, we want to write in terms of x1 dot, so therefore I'll write x1 dot is equals to u, and then minus 7x1, because I bring this over this side, right? And then minus 12x2. Right, so minus 7x1 is simply minus 7 times x1, minus 12x2 is simply minus 12 times x2, plus 1 times u over here. Okay, and you know that your x dot 2 is equals to your x1. Your x dot 2 equals to x1, and therefore I'll just simply write as 1, and there is no other thing that can represent s2 dot, because it's x1 only, so therefore this is zeros over here. Alright, why this is 0 is because your x1 dot is simply represented by your u, by your x1 and x2, so therefore I can rewrite all this here. But as for x2 dot, this is simply x1 only, so therefore there is no u or whatever, so these are all zeros. And these are only for ax plus bu. Okay, so what about cx plus du? Same thing, my x is your state system, alright, plus du. Okay, so this is your cx plus du is equals to output. And your output only is what? 2x2. So therefore what we have is 2x2 is equals, maybe I should write it over here, y is equals to 2x2. Alright, so 2 times x2 is simply 2 times x2. There is no x1, so therefore it's just simply 0. Okay, I hope you get what I mean, because y is equals to only 2 times x2. So there is no x1, so 0 times x1 is a 0. Alright, so therefore 2x2. And then there is also no in terms of input, so therefore this thing over here is always 0. So what we left over here is just simply this one, your output. Okay, so therefore this is all your state space already. As you can see, we have go through all these processes to do this thing. So how does canonical form help us? Or how does the general canonical form help us? So we use this notation, b and a, as you can see. For the denominator, ensure that your first value is 1. Right, it's a monic system if you remember. So therefore, this is s squared, there is only one coefficient. So when you want to use your canonical form, make sure that your this thing over here is always 1. Alright, please remember that. So we use this, alright? In our case, this general equation is simply what? It's simply only b1. Okay, why do I say only b1? Because it's only s to the power of 0. Alright, so this is only s power of 0, so this is s power 1, and so on and so forth, s to the power of 2, etc. to s to the power of n minus 1. Alright, I'll not go into details of those stuff, but in this case, we are talking about only b1. Alright, and your Sn is simply your x squared. Alright, this is some other stuff, we'll just leave it because we have no other series, so I can simply bring this in. Aha, so as you can see, our general equation for our this thing over here is simply this. Alright, so the next thing is what? Alright, we're gonna take out this canonical form, open loop one, and I'll just paste it over here. Okay, and then I'll just copy this thing and paste it over here. Maybe I should rearrange all around. Alright, so what we have now is this thing. Okay, we have only a2 and a1, right? So the canonical form over here, this is a general canonical form all the way to an, you see. So therefore we only have a1 and a2, and therefore I can just simply remove away the rest of these matrices. Okay, where we only have 2 times 2 matrix. So we have this thing over here. Alright, because we only have a1 and a2. Alright, and then for a2 over here is your 7. Alright, however we are going to write, and I just found something. I just want to share with you because this is also a good understanding for you not to memorize straight away from the canonical form. Why is that? Why do we say so? Alright, your a2 over here, alright, see a2 is equals to 7, for example. So in the canonical form we can say that it's minus a2, so you can write it as minus 7. For a1 is equals to 12. Alright, we're seen over here. So minus a1, so I'll just simply write as minus 12, right? Because it's the standard minus your a1. Your a1 is 12, so minus 12. Alright, if you were to compare back to our just now that one, ours is what? Minus 7 minus 12. You see? Okay, so therefore what I can propose is that this thing over here should be rewritten over here like this. So be very careful of how do you sub in your stuff, because the canonical form, alright, over here doesn't correspond to the general equation over here. A general thing, if you were to want to remember this form, okay, I'll recommend you write in terms of what? Alright, this, remember that this is an minus 1, this is an minus 2, this is all the way to an minus whatever value, infinity. Alright, as you can see, this value, alright, the very first value I should write as an, sorry. Over here this should be an, this is an minus 1 all the way blah 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 blah, all the way to an minus infinity. Okay, your an over here is your an over here. Corresponds, maybe I should zoom out, maybe I should copy this. Yeah, I should copy this better. Alright, as you can see, your an is simply this one, and then blah blah blah, you all the way sub in over here. That's is going from n all the way to a smaller number, n minus something, or n in this case is dependent on your order over here also. I think you get what I mean already lah, okay? So therefore, please remember that when you remember the canonical form, this is not somewhat the case. Alright, this is an, and then this is an minus 1, and things like that goes on. Okay, so this is one form that I find that need to be shared with you. Alright, same thing over here. This one can be also rewritten as bn minus 1 all the way to bn minus infinity. Okay, please be very careful of that. Same as for your k, etc. Okay, n minus infinity over here. Alright, so therefore, as you can see, although somewhat don't take this as a problem, but take this as a learning, and note that this thing over here, the purpose of the canonical form is to help us write your state space in a more easier way. Alright, because you can simply sub in your, you know that your A1 now, alright, this is your okay, your A2 now is simply 7, alright, your A1 is simply 12. Okay, so you can straight away sub in your A's into your canonical form. Alright, I should just switch this also over here. Okay, so therefore, as you can see, your A1 is equals to 12, so minus 12 and minus 7. Alright, so you can just simply take this, know this form, this general form, and then you just simply plug in the constant, just sub it into the state space, and that's it, straight away, straightforward. You don't need to do any stuff. So the good thing for this shortcut method is for you to sub in easily without going through all these processes that we have discussed earlier to do all the stuff. You can just simply sub it in only. Alright, but because of the problems between the different understandings, alright, between this thing over here and this things over here, there's a little crash of the understanding. So therefore, you need to know how to articulate with your answers, because you may end up writing two different stuff. Alright, so be very careful of these things. Alright, and that I think I'll just leave you to this thing, because later on we'll use these understandings to continue to do other stuff. Alright, so therefore I'll see you there in the next video.